This is the Faraday's Law and Lenz's Law demo set. To understand electromagnetism, you first need to understand Faraday's Law. Faraday's Law describes the interaction between moving magnets and coils. Moving magnets create forces on electrons, and moving electrons create magnetic fields. This is a difficult and abstract concept for students, but this exclusive product from Arbor Scientific is designed to capture their attention. What do you suppose will happen when I drop a magnet through this thick copper collar? As the magnet falls, its moving magnetic field induces a current in the copper collar, and most of its kinetic energy is transferred into electrical energy. This transformation from mechanical energy to electrical energy is called Faraday's Law. This same effect, called electromagnetic induction, is the operating principle of all electric generators and motors. Now, what do you suppose happens if I flip the magnet? Nothing changed, but why is that? Lenz's law states that induced current opposes the change in magnetic flux, so the current's magnetic field is opposite to the falling magnetic field. Wouldn't it be nice to see what's actually happening inside the copper collar? Now you can. We developed this new apparatus in collaboration with the physics teacher who asked the same question. This apparatus and the pedagogy will help students construct a conceptual understanding of Faraday's Law. It consists of a plate with an exposed circuit that is designed to integrate a solenoid. So when a powerful magnet is dropped through the solenoid, the green LED on the circuit board lights up to indicate the direction of induced current. Moving a magnet near a coil causes a push on the electrons. With the solenoid attached to the circuit, the LEDs allow current to flow in one direction but not in the opposite direction. And now we can be certain that the falling magnet pushed or pulled electrons in one direction around the solenoid. But suppose we repeat the experiment, this time reversing the pulls on the magnet before dropping it. The green LED flashes again, but why is that? Since the current should only be going in one direction. Let's hang on to that question for a second. Now let's include the red LED into the circuit and repeat our experiment. Now both LEDs are flashing, but not at the same time. In case you didn't catch that, the green flashed before the red. Now let's flip the magnet again and see what happens. The LEDs are now flashing in the opposite direction. To quantify what's happening inside the wires, you can connect a solenoid to a voltage probe and display a graph of voltage over time. Set the collection rate at 1,000 times per second and a time interval of 1 second and drop the magnet. Repeat the drop and ask students to share their observations. You can see that the current flows first in one direction and then in the other. This is a really important confirmation of what students should be predicting from the flashing lights. If you reverse the magnet, it reverses the order of the LEDs and the peaks of the graph. Not only is this a great way to demonstrate Faraday's Law, but it also helps answer one of the most common questions in AP Physics class. The ready-to-go construction and all-in-one nature of this set create a clear pathway for students to better understand a challenging topic. The Faraday's Law and Lenz's Law complete demo set comes with a plastic guide tube, a custom circuit plate, a thick copper collar, banana plugs, a giant neodymium magnet, an impact pillow to protect the magnet, and a 5 amp max air core solenoid. If you already have an air core solenoid and a large neodymium magnet, the Faraday's Law and Lenz's Law base demo set might be what you're looking for. If you want to learn more about this and other cool stuff, visit arborsci.com.